This is the 5.3 video for conditional probability and independence. When you see conditional probability, conditional distributions. And as we go through this, think how those two are related. Remember that a conditional distribution had values of two variables on the two-way table. And given that one other occurred, what were the probability of a second variable of the various values it could take on? And that's exactly what conditional probability shows. So if you think along the lines of that conditional distribution, that should make things a little easier as you go through this. That tends to be one that's a little bit tougher. So, guiding questions. Using our general multiplication rule, which we'll go through, and conditional probability formula, how do we calculate the probability of two events both occurring? How does this change if they're independent? What does it mean to say events are mutually exclusive? As I said in class, focus on that independence versus mutually exclusive. It's extremely important, and they're often confused. Conditional probability, we write our notation like this. This means the probability of event B occurring given, that's what the vertical line is there, that A has already occurred. That means A happened, now what's the probability of B? Remember that independent events, one occurring doesn't affect the probability of the other. So we would write down here, we would write the probability of B given A is the same as the probability of B if they're independent, meaning A occurring had no effect on whether the probability of B occurring. That just means the two events are independent. So if one occurrence affects the other, then these two probabilities down here are not equal. So keep those things in mind as we go through this. A conditional probability, conditional distribution, since it's the probability of the value of one variable given the specific variable of the first. So independent events, as I said, the probability of B occurring is not affected if A occurs. That means events A and B are independent. Event A happening doesn't change the probability that B occurs. That's the definition mathematically of independence. The idea is that one outcome of one event doesn't affect the likelihood of another occurring. And we're saying the same thing by showing this. So examples of independent events are rolling a die. The outcome of the first roll has no effect on the outcome of the second roll. We could roll 10 sixes in a row. It's still a 1 in 6 chance of rolling a 6 on the 11th roll. If they're independent, if they're not independent, that does not mean there's association between them. So if the probability of A given B is close to the probability of A, but not equal, so if they're close, then the two events are not technically independent mathematically, but there's not an association between the two. So if the probability that an event occurs is drastically different given another event occurring, so if the probability of event A occurring is changed quite a bit by B occurring, then we might look into there being an association between the two. If they're close, then it's not likely that there's an association between the two events, but we cannot define them as independent. So those two probabilities have to be equal. So the probability of an event cannot be changed if we're to consider them independent. For independent events, we can set up a nice tree diagram. This is to illustrate the general multiplication rule. The event is here, tossing a coin. Here we're looking at a first toss and a second toss. And we're calculating the probability of each set of outcomes. Now my sample space would be following each branch. Heads, 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 tails, tails, heads, tails, tails. So if I want to find the probability of any series of outcomes, I can follow my tree diagram. Because these are independent events, 1/2 is the probability of heads on the first and the second toss. So if I want to find the probability that I get 2 heads, as illustrated here, I follow this 1/2, and then I multiply by 1/2 equals 1/4. And right here, I'd write probability of H comma H, or 2 heads, and I'd write this out at the top here. And you could write on the right all the values. So this is a very simplified one where they all equal 1/4. However, when we get into more complicated problems, this will be very key to look at. So we call this a tree diagram. We're going to be drawing these a lot to guide our work in probability, and they make all of your problems much easier. This helps us determine the sample space by following each branch and each individual outcome, especially if our numbers aren't so clean as tossing a coin. We'll write the chance process again here on the left, and then we split it into different outcomes on the right, depending on how many repetitions of a certain event we have. So let's look at some notation. So remember that intersection means both happen, like when the intersection of two streets, both streets are there. So the intersection of Van Ness and Turk, you're on both Van Ness and Turk. So the intersection of two events, both events are occurring. The union would be the U, and that would be represented as either occurring. So you could be on either Turk or Van Ness. That's going to have a larger probability, because either can occur. So the intersection, the probability that they both occur, is the probability of A times the probability of B given A. So we multiply in order to see the probability that two events both occur. Now remember, if the events are independent, then the probability of B given A is going to be the same as probability of B. So this, if they're independent events A and B, this can be simplified to probability of B, because that's the definition of independence, that the probability of B given A, that A occurring has no effect on B. Now note that this is in order, because if this were different, if it were affected by the probability of A, then this value would be different. So whatever the first occurrence is, and then the conditional probability to multiply. So if they're independent, we just multiply. Probability of A times probability of B. In the example there, that was 1/2 times 1/2, or 1/4, is the probability of flipping two heads on two coin tosses. And again, we're saying that this first event must occur, and then this second one, which is why this is written as a conditional probability, but with independence, that simplifies to probability of B. Now here's a huge tip to save you a lot of headaches, and it's really actually a cool thing about just logic here when we're solving these probability problems. If you see a question about the probability of at least one, that can be a series of outcomes. So if we have 10 different possible events repeating, and we say a probability of at least one, that could include 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all occurring, like at least one heads or at least one tails at 10 coin flips. That's a tedious process to add up all of those. So if you see at least one, think of the complement. The complement is that something doesn't occur. So the complement of at least one is the probability of none. If none occur, then we subtract it from 1, because that's 1 represents 100% of the time or all outcomes happening. Then we can find the probability of at least one. So think shortcut here. If you see the probability of at least one event happening, you say, okay, I'm going to find the probability that that it happens 0 times, and then subtract that from 1, because all other outcomes other than no events are at least 1. You can use that logic also for at least 2, but then you'd have to subtract 1 minus probability of no events minus 1 event. So for a series of repetitions, and if you see at least one, think subtracting from the complement. So down here we see at least one heads, we do probability 1 minus probability of 10 tails, which is easy to come up with, 1/2 to the 10th. We subtract, and we get about 99.9% of the time we would get at least one heads. So I want you to use that logic for your multiple choice question now. So here we have an athlete suspected of using steroids, given 2 tests that operate independently of each other. Remember, that means the outcome of one doesn't affect the outcome of the other. Test A has a probability of 0.9 of being positive if steroids have been used. Test B has a probability of 0.8 if steroids have been used. What's the probability that neither test is positive if the athlete has been using steroids? So we're given the fact that he's been using them, and then we're saying test A has a probability of 0.9 of being positive, test B is the probability of 0.8. We want to know the probability that neither test is positive. In other words, what's the probability that the athlete does steroids, takes both tests, and still tests negative? Here's a little hint. You're given the probability of testing positive for both tests, so think about what the probability is of testing negative, and think about the rule, the multiplication rule for independent events. Pause now, submit your multiple choice, and then we're going to continue with the video and your free response. Here's a huge concept, mutually exclusive versus independent. We talked about independence. Let's look at what mutually exclusive means. Mutually exclusive means 2 events do not occur. If event A occurs, then event B does not occur. So the probability that if event A is defined as attending school and event B is defined as being absent at home all day, then the probability of both those 2 events are mutually exclusive. If you're absent at home all day, you cannot be present at school all day. So if absent at home all day occurs, the probability, the conditional probability is then 0 that you're going to be at school. Vice versa, if being at school all day occurs, the conditional probability that you're absent at home becomes 0. Mutually exclusive, they cannot happen. Because that changes the probability of the second event to 0, they are not independent. Mutually exclusive events are never independent, because one happening changes the probability of the second to 0 of occurring. So that's super important to remember. So event A, here's another example, a person is born male. Event B, a person is pregnant. They can't both occur. If you're born male, you cannot get pregnant. So if we know event A has occurred, a person is male, then we know event B cannot occur. That means they're not independent. If we know event B occurred, the person is pregnant, we know event A could not have occurred. So when one of these events occurs, it reduces the probability of the second one to 0. That means they're not independent, and because they both cannot occur, they have no intersection. The two Venn diagrams would be two circles next to each other in the sample space with no common outcomes. Okay, we're going to go over your free response question here, and then you're going to have one more little bit of the video to watch that's very important as well on conditional probabilities. So here we have a student applying to UC Berkeley as her top choice, and she also knows she needs to get a job as an intern at this place. And she decides, given her history as a student, she has a 71% chance to get into UC Berkeley, and that a 45% chance of getting this job in her first month. So assuming the two events are independent, what's the probability that she gets into UC Berkeley and gets hired? What does it mean to say that they're independent? And then are they mutually exclusive? Why or why not? Pause now and answer the free response, and then continue with the video. Now here's a nice example from your book that you should look over about the conditional probability formula. So it's kind of like working backwards in the tree diagram. So the probability of B given A, that means event A has occurred and now event B is going to occur. So we think about the intersection as being multiplying the two. So try if you can see if you can look through our tree diagram. One outcome would represent the probability of the second event happening given the first. And this is like working backwards through the tree diagram. So we'll look at this in class too with a visual. So right now, go over 5.3, the summary, vocabulary, and look over the examples. This is a more challenging section, so I encourage you to really put in some work now so you can come to class with questions and set yourself up for success for the quiz and the chapter test.